Hello dear students, this is Sindu KOUSHIK. So in the previous video, I explained what do you mean by algebra of a set and also two propositions related to algebra of a set. So in this video, I will explain the concept sigma algebra, that is Boral field. Let us begin with the definition sigma algebra. Here is the definition. An algebra A of sets is called a sigma algebra or a Boral field if the condition is, first of all, it must be an algebra. The condition is if every union of countable collection of sets in A is again in A. What it means? It is closed under countable union and also closed under countable intersection. So it is closed under countable union. For algebra of a set, it must be closed under finite union. For to be a sigma algebra, it must be closed under countable union. So what it says? The collection A of subsets of X is said to be a collection A of subsets of X is said to be a sigma algebra. Said to be a sigma algebra if it satisfies conditions. So first one is this collection must be a algebra. This collection must be a algebra. Second condition is if you consider ANs A1, A2, so on ANs in A, then whose countable union, that is n varies from 1 to infinity. So 1 to infinity means what? 1, 2, 3 up to infinity is nothing but a natural number. Natural number is a countable set, or Z plus is a countable set. Therefore, it is a countable union. So which is clearly belongs to A. So say that when we say that the collection A is a sigma algebra, that collection must be an algebra. Algebra means it satisfies two conditions. First condition is it is closed under countable union. If you consider two sets, then their union must be in A. That is, it is closed under countable union and it is closed under complementation. If A belongs to, whenever A belongs to A, whose complement is also belongs to A. So, and also one more condition is what? It must be closed under countable union. It must be closed under countable union. Union of A and n from 1 to infinity, which is also belongs to A. Then we say that that collection is a sigma algebra. Is it clear? So now let us take an examples for that. So here is an example, power set. So in the previous video I explained the power set is an algebra. So algebra of a set, this is over. Next condition is what? We check for this condition whether the P of X is closed under countable union or not. For that I am considering the sequence, that is a sets in P of X. P of X is nothing but power set. It means what? It contains collection of all. The P of X is the collection of all subsets of X. So AN is belongs to P of X means what? AN is a subset of X. If AN is a subset of X, it means what? Union of AN is also a subset of X. In fact, countable union of AN is also a subset of X. If it is a subset of X, it means what? Union of AN clearly belongs to P of X. So here I am considering ANs. I am getting union of ANs, which is in fact countable union of ANs clearly belongs to P of X. Therefore, P of X is a sigma algebra. So P of X is first of all algebra and also satisfy the one more condition which is closed under countable union. Therefore, it is a sigma algebra. So next example, empty set and whole set. The collection A contains empty set and whole set, then which is also a sigma algebra, because if you consider the union, we get the whole set. If you consider the complement, we get the X. If you consider the complement of X, we get empty. So therefore, which is clearly belongs to A, that collection. Okay, so therefore it becomes an algebra of a set. So here we have only two sets. If you consider the union of these two sets, then we get X, which is clearly belongs to A. Therefore, it is closed under countable union also. So therefore, it is a sigma algebra. So next, here is the remark. Every sigma algebra is an algebra of a set. But algebra of a set need not be a sigma algebra. Every sigma algebra is an algebra. Why? Because the definition itself says sigma algebra, first of all, it is an algebra. But an algebra of a set need not be a sigma algebra. Need not be. Here is the need not be word. It means you must have the counter example to show that collection must be algebra but not a sigma algebra. So for that I will explain later. Very small note. What is that note? By De Morgan's law, it follows that intersection of a countable collection of sets is in A. That is intersection. So sigma algebra definition says it is closed under countable union. By De Morgan's law, we can also say it is also closed under countable intersection. It means if you take the complement of that, it becomes what? N from 1 to infinity, which is also closed under countable intersection. So this is because by De Morgan's law. Next. Here is the proposition. Given any collection C of subsets of X, there is a smallest sigma algebra which contains C. In the previous, for algebra of a set, we have the proposition similar to this. That is, given any collection C of subsets of X, there is a smallest algebra which contains C. So where we have proved, so this is what? This is the proposition. So what is that proposition? Given any collection C of subsets of X, there is a smallest algebra A which contains C. Here smallest algebra. Okay. So and the proposition for smallest sigma algebra, both are same. Just change the family of, here I am considering the family of algebras. Just change this family by collection of all sigma algebra. And also show that it is also closed under, and here is, and also show that collection A which is closed under countable union. Then the proof of that proposition is over. Is it clear? So this is very important proposition for the definition Boral set. So given any collection C of subsets of X, there is a smallest sigma algebra which contains C of subsets of X. Any collection C of subsets of X means subsets of, you can take for X R, subsets of R, you can take intervals, anything. So it must be a subsets of the set X. Okay, so here is an example of an algebra of a set which need not be a sigma algebra. For that, I am considering X is equal to R, set of all real numbers, and the collection A is equal to set of all A be a subset of R, that is a subsets of R, such that that subset must be a finite set or whose complement is finite. So when that set belongs to the collection A, if you consider the set A, if it is finite, then it is clearly belongs to A. Or whose complement is finite, then it is clearly belongs to A. So this is the collection. Okay. So here I am considering some examples. That is, singleton 1 is a member of A. Why? Singleton 1 is finite, therefore it is a member of A. Here 1 to 100, the set containing 1 to 100, clearly this set is finite since it is A is finite. If A is finite, then we say that A belongs to A. Here 1 to 100 is finite, therefore it is clearly a member of A. Next, R minus singleton 0 is also a member of A. But R minus singleton 0, which is not a finite set, why it becomes a member of A? Reason is whose complement is singleton 0. So whose complement is singleton 0 is finite. Therefore, it is a member of A. Is it clear? So to be in A, either the set is itself finite or whose complement must be finite. Is it okay? So this is the collection. So we show that this collection is an algebra of a set, but not a sigma algebra of a set. To show that it is an algebra, what is the conditions? First condition is it is closed under finite union. Second condition, it is closed under complementation. So I am first considering the second condition. First, here I am considering the A belongs to A. So A belongs to A. It means what? When it belongs to A, the collection A. So the set A belongs to A means either A is finite or A complement is finite. So A belongs to A implies either A is finite or A complement is finite. So what we have to show now? Here I am considering A belongs to A. So we show that A complement is, we show that A complement is belongs to A. Then A becomes, it is closed under, then A becomes, it is closed under complementation. So for that, to be A complement is in A, what is the condition? A complement is finite or A complement whole complement is finite. So what is the condition? Either A complement is finite or A complement whole complement is finite. So what is that? A complement is finite, that's okay. Or what is A complement whole complement? A is finite. A complement is finite or A is finite is nothing but A is finite or just reverse, A complement is finite. So here we have this. Here either A is finite or A complement is finite is nothing but either A complement is finite or A complement whole complement A. So which is clearly finite. Therefore it is closed under complementation. Is it clear? So next, the second condition. What is the second condition? We have to show that if you consider AB is in A, you have to show that A union B must be in A. So here, so what is the collection A says? The collection A is a subset of R such that A is finite or A complement is finite. Okay. So for the second condition, so I am considering AB belongs to A. So AB belongs to A means what? Either A is finite or A complement. Either A is finite or A complement is finite. B belongs to A means what? B is finite or B complement is finite. So, or we have some cases like both are finite, both A and B is finite, or A complement is finite or B complement is finite. I am considering the case A and B finite. Both are finite, and I am considering the second case A complement or B complement is finite. So what is the our claim part? So we have to show A union B must be in A. So to be in A, so what is the condition for that? To show this one, for that we must show A union B is finite. To be in A, what is the condition? A union B is finite or A union B whole complement is finite. Okay. So now, here I am considering the case both A and B are finite. Either A complement or B complement is finite. So we now show that either A union B is finite or A union B whole complement is finite. So for that, for the first case, for this case, both A and B are finite. It means what? A union B is clearly finite. For the second case, A complement or B complement. It means what? A complement. R means intersection and means union. A complement intersection B complement. What it says? A union B whole complement. A complement intersection B complement is nothing but A union B whole complement. Is it clear? So take the complement A complement. Okay. Union complement is intersection. That's okay. B complement is that B complement itself. Therefore, they are equal by De Morgan's law. So clearly it is finite by using second case. From the first case, we obtain A union B finite. From the second case, we obtain A union B whole complement is finite. So A union B clearly belongs to A. So A is an, from two condition, it satisfies two condition of algebra of a set. Therefore, A is an algebra of a subsets of R. Now, we now show that it is not a sigma algebra of a set. So to show that it is not a sigma algebra of a set, to be a sigma algebra, that must be an algebra or it must be a closed under countable union. Here it clearly holds A is a sigma algebra. So we now show that whose countable union does not belongs to A, then it becomes not a sigma algebra. For that, consider A1, A2, AN. So first I am considering A1, A2, AN. A1 is singleton 1. So which is clearly belongs to A. Why? Because singleton 1 is finite, therefore it is belongs to A. So A2, singleton 2, finite, therefore belongs to A. AN, singleton n, finite, therefore belongs to A. So this one, all are belongs to A. All are belongs to A. What about the union of these collection? What about the union of these sets? Union of these set is 1, 2, 3, so on. 1, 2, 3, so on is nothing but a natural number, set of all natural numbers. Or you can say positive integers. So union of AN is a set of all positive integer, but union of AN, this positive integer does not belong to A. Why? Z plus, which is not a finite set. In fact, whose complement is what? R minus Z plus, which is also not a finite set. That set itself is not finite, whose complement is also not finite. Therefore, it is clearly does not belongs to A. So we conclude that A is not a sigma algebra of a set. Is it clear? So next problem. Let's see with the collection of all intervals in R of the type open, closed, open, and open, closed, open race. Is it okay? So this is a collection of all intervals in R of the type. Then there exists a, according to the proposition, then there exists a smallest algebra A which contains A. And it is easy to check that A is this collection which is not a sigma algebra. This collection, it is easy to check that A is not a sigma algebra. So for that, claim is A is not a sigma algebra. So choose A1, A2, AN. So I am considering open closed interval. Here open closed interval is clearly belongs to that collection. Therefore I am choosing open closed, open closed, open closed. Clearly belongs to A. Okay. So now 2 minus 1 by 1, 2 minus 1 by 2, 2 minus 1 by n. Clearly an belongs to A for n is equal to 1 to 3. What about the union? Union of an is n from 1 to infinity. Union of n from 1 to infinity. Union. So union of this one becomes what? So take the union first. So first one is what? 0 minus 2 minus 1 by n for an. For first one, a1. What is that 1? If you put 1, 2 minus 1 by 1. So 2 minus 1 is what? 1. So clearly 0, 1, 2. So clearly 0, 1. 0, 1. Next, what is A2? 0, just substitute 2 here. 2 minus 1 by 2. 2 minus 1 by 2, that is closed interval, sorry. So 0. 2 2s are 4. 4 minus 1 is what? 3 by 2. So 3 by 2 is what? 2 1s are 2, 1.5. So 1.5 is here. So open 1.5 up to 1.5. Next, if you take A3, then 2 minus 1 by 3 closed. So 0. 3 2s are 6. 6 minus 1 is what? 5 by 3. 3 1s are 3. Point here 2 remains. 3 6 are 18. 1.6. So 1.6. So like that up to what? Say if you take infinity. Infinity is what? 0. 2 minus 1 by infinity. 2 minus 1 by infinity is what? 2 minus 1 by infinity. We don't know the infinity value. For that I am considering open interval. So 1 by infinity is 0. That is 0, 2. So clearly this union of an becomes what? Union n from 1 to infinity. Open at 0. Open at 0 and open at 2. So union n from 1 to infinity 0 to 2 minus 1 by n is 0 to 2. Why? The reason is, so to show that it is equal to 0, 2, when the two sets are equal, if A is subset of B and B is subset of A, then they are equal. So for that, here 0, 2, here union of an is clearly a subset of 0, 2. Why? Because 0, 2 minus 1 by n is clearly contained in 0, 2. So why? Reason is 2 minus 1 by n means what? Here we have 2 minus 1 by n. So 0, 2 minus 1 by n is clearly a subset of 0, 2. Is it okay? 2 minus 1 by n is little smaller compared to 2. So therefore 0, 2 minus 1 by n is a subset of 0, 2. So here is this one is an is subset of, therefore union of an is also a subset of 0, 2. Mark this as 1. We now show the reverse. What is the reverse? 0, 2 is contained in union of A and n from 1 to infinity. So why I am considering this? So to show that this one, union of an is equal to 0, 2. That is union of this one is equal to 0, 2. Why it is? So now opposite, that is to show that A is subset of B, take an element x belongs to A. Show that x must be in B. So here I am considering in A, but we get in B, then it becomes a subset. A is a subset of B. For that I am considering in this set 0, 2, that is x belongs to 0, 2. X belongs to 0, 2, it means what? X is in between 0 to 2. Is it clear? So x is between 0 to 2. Now take this part. X is less than 2. X is less than 2. Take minus x on both sides. Subtract x on both sides. Then x minus x, 2 minus x. X minus x is 0, less than 2 minus x. So we get 2 minus x is positive. So mark this one has put x is equal to 2 minus x and y is equal to 1. Why? Apply Archimedean postulate. What it says? For positive real and a real, there exists a positive integer n such that nx is greater than y. So here the positive is 2 minus x and for y I am considering 1. So nx is greater than y. N into 2 minus x greater than y is 1. So 2 minus x is greater than 1 by n. So from this we get 2 minus x is greater than 1 by n. Or you can say x is less than 2 minus 1 by n. Here I am considering this. Next, x is less than 2 minus 1 by n. So x is less than 2 minus 1 by n means what? X is belongs to. So here note that x is greater than 0 and less than 2 minus 1 by n. It means what? X is belongs to the interval 0, 2 minus 1 by n. In fact, this closed interval. Why? Because x is greater than 0, less than 2 minus 1 by n means it is belongs to the open interval 0, 2 minus 1 by n. But it is a subset of 0, closed at 2 minus 1 by n. So clearly it is x is belongs to the subset means x is also belongs to the superset. That superset is what? 0, 2 minus 1 by n, which is an. So x belongs to an. It means what? X belongs to union of n from 1 to infinity. So therefore, where we consider x in 0, 2, where we get union of an. Therefore, 0, 2 is subset of union of n from 1 to infinity. Mark it as 2. From 1 and 2, we conclude that union of an is equal to 0, 2. But this 0, 2 does not belongs to a. Why? This collection, which contains only the minus infinity closed at a and b open at infinity and open closed interval, which do not contain the type of the interval, say a comma b, the open interval a comma b. So 0, 2 is of the form a comma b, so which is not in that collection, therefore which is not in the collection a. So ans are belongs to a, but union of ans does not belongs to a. It means what? It is not a sigma algebra. Next concept, Boral sets. So here, next concept, Boral sets. So what is the definition of a Boral set? So here, let C be the set of all open subsets of R. Here I am considering the collection C be the sets of open subsets of R. Now, by the above proposition, what we get? By the above proposition, what proposition says? Given any collection C of subsets of X, there is a smallest sigma algebra which contains C. So for this collection also, we get a smallest sigma algebra. There always exists a smallest sigma algebra, say B, cursive B, which contains C. Okay. Then the elements of B are called Boral sets. So, thus the collection B of Boral sets is the smallest sigma algebra which contains C. C means what? C is a collection of all open subsets, therefore which contains all open sets. So, is it clear? Okay, let us explain. Okay, let me explain once Boral set. So, to understand the definition of Boral set, take the collection C of what? Collection of C of subsets of R. In fact, open subsets. Here, the C be the set of all open subsets of R. C be the collection of all subsets of R such that A is open. Means the collection of all open subsets of R. And for this collection, by using the previous proposition, what it says? For a collection of C of subsets of X, there always exists a smallest sigma algebra. There exists smallest sigma algebra. Smallest sigma algebra, say cursive B, which contains C. Which contains C. Means C is contained in B. What about B says? B says smallest sigma algebra and contains C. C is what? Collection of all open sets. Open subsets of R. So it means what? B is the smallest sigma algebra which contains all open sets. Which contains all open sets. So what is that B? B is the smallest sigma algebra which contains smallest sigma algebra. Smallest, very important, sigma algebra which contains all open sets. This is the collection B. This is the collection B. The elements of this collection is nothing but Boral sets. Is it clear? The elements of this collection is nothing but a Boral sets. So if B is nothing but is a collection of, if the collection contains say A, B, C, then A, B, C are all Boral sets. The elements of this collection is nothing but a Boral sets. So what do you mean by a Boral set? Boral set is nothing but an element of the cursive B. That cursive B is the collection which is the smallest sigma algebra which contains all open sets. Now, is it clear? Thus, the collection B of Boral sets is the smallest sigma algebra which contains all open sets. So, this is very important. Next, what is the remark? By the definition of a sigma algebra. So, sigma algebra means what? It must be algebra and also it is closed under countable union. So, it follows that the collection B of Boral sets contains all closed sets also. Why? Since B is a sigma algebra. Sigma algebra means it also a algebra. Algebra means B is a smallest sigma algebra. Sigma algebra means it is a algebra. First of all, it is a algebra. Algebra means it satisfies two conditions. First condition is finite union. It is closed under finite union and closed under complementation. Okay. So here the cursive B is the smallest sigma algebra and also contains open sets. So open sets means which is an element of B. Open sets are, which contains open sets means open sets are elements of B, but B is a sigma algebra. It means what? It is closed under complementation also. What is the complement of open set? Complement of open set is nothing but closed sets. So closed set clearly belongs to B. Since it is a sigma algebra, therefore it is also contains closed sets. By the definition of a sigma algebra, it follows that the collection B of Boral sets contains all closed sets. Is it okay? So next example is open closed interval 0, 2 is a Boral set. This is the question. Is open closed interval is a Boral set? Answer is yes. Why? 0, 2 can be written as 0, closed at 2 can be written as here. Look at here. The open interval 0, 2 union singleton 2. So this is an open set. Singletons are closed sets. Is it clear? Open sets are Boral set. Closed sets are also Boral sets. So union is also belongs to that collection B. Why? Since it is a sigma algebra which is closed under finite union also. Therefore, it is an element of B means what? Which is an element of B means what? It is a Boral set. So why Boral set 0, 2 can be written as open 0, 2 union singleton 2. So this is open set. So therefore belongs to B. This is closed set. The closed set is also belongs to B because that Boral set also contains closed sets. Then, so union of these two is also belongs to B. Union of these two also belongs to B. Why? Because it is a sigma algebra. Sigma algebra means which is an algebra. Algebra means which is clearly closed under countable union. Here is the union. So union of these two elements is also clearly belongs to B. So belongs to B means what? 0, 2 is clearly belongs to B. Belongs to B means what? The elements of B are nothing but Boral set. Therefore 0, 2 is Boral set. Is it clear? So next, second condition, second problem is Q is a Boral set. Next question is Q. Q is a set of all rational numbers. Is a Boral set? Yes. Why? Q is countable. You know that the set of all rational number is a countable set. You studied in the real analysis too. Q is a countable set. So we can arrange the elements of Q as a sequence of distinct terms. So that is Q can be written as union n from 1 to infinity singletons Rn's R1, R2, sequence of distinct terms. So countable union of which is clearly belongs to B. So because singletons are closed, clearly belongs to B. Since B is a sigma algebra which is closed under countable union, therefore this countable union is also belongs to B. So what is this? This is Q. So therefore Q is Boral set. So every countable set is a Boral set. So Boral set. Next, what about irrationals? Set of all irrational, is it a Boral set? Yes. Why? So I is a complement of Q. So complement of Q. Since Q is a Boral set, Q is a Boral set means what? It is an element of B. Since B is a sigma algebra means which is an algebra. Algebra means which is closed under complementation and also which is closed under finite union. So complementation. So because of this condition, complementation, Q complement is also belongs to B. What is the Q complement? Is nothing but I. I is belongs to B. So I is an element of B means what? B is the elements of B is nothing but a Boral set. Therefore I is also a Boral set. Collection of irrational numbers. Next. So every element of I is also in Q complement. Since Q is a Boral set, I is also a Boral set. That is over. Note every interval is a Boral set. So please do remember every interval is a Boral set. Next definition. F sigma set. So what it says, F sigma set. A set which is a countable union of closed set is called F sigma set. The set, if it can be written as a countable union of closed sets. I am considering here F. Closed sets. Countable union n from 1 to infinity. Then we say that that set is a F sigma set. So here F sigma, the symbol which is originated in France, here F stands for firm and sigma stands for SAM. Firm stands for closed and SAM stands for some union. So here F sigma, F stands for closed and sigma stands for union. So what it says, F sigma set says, F stands for closed, sigma stands for union. So F sigma is nothing but countable union of closed sets. That's it. So here is the example. Q is an F sigma set. Q is a Boral set. Q is an F sigma set. So why it is an F sigma set? In fact, every countable set is an F sigma set. So in Tikhonov space, each countable set is an F sigma set. Tikhonov space, so you studied in topology. So where in Tikhonov space, every countable set is an F sigma set. Now, so let us understand why Q is an F sigma set. Q can be written as countable union of singletons, where singletons are rationals, union n from 1 to infinity, distinct elements. Why it can be written as like this? Because Q is countable. According to the definition of countable sets, every elements can be written as a sequence of distinct terms. So distinct terms is R1, R2, R3. So n from 1 to infinity, that is Rn. Rn's are what? Closed set. Therefore, it is what? It is a countable union of closed sets. Therefore, it is a F sigma set. Is it clear? Now, what about open interval 0, 2? Open interval 0, 1. So, open interval 0, 2 is the countable union n from 1 to infinity of the closed interval 1 by n and 2 minus 1 by n. To 1 by n. 1 by n, 1 by infinity is 0. So for that we don't know the infinity value. So take open 0. Here 0 is open and 2 minus 1 by n. So here if you consider infinity, 2 minus 1 by infinity is what? 0. 2 minus 0 is 2. So for that here open interval 2, not closed. So therefore it is clearly, it is a countable union of closed interval. Countable union of closed sets. So therefore it is a F sigma set. 0, 1 is also. Here n varies from 2 to infinity. Why? If you consider 1 here, then it becomes 1. Then it becomes 1. Okay. So in general, A comma B. In general, A comma B union n from 1 to infinity can be written as A comma P can be written as countable union of closed at A plus 1 by n and closed at B minus 1 by n. Take little small, take little large, that is little large compared to A, little small compared to B, that is A plus 1 by n and B minus 1 by n, provided A plus 1 by n is less than B minus 1 by n. So why it is equal here? I am not explaining this reason. Have a look here. Next, complement of F sigma sets are nothing but G delta set. Complement of F sigma sets are nothing but G delta set. So now the definition of G delta. So what it says, if you consider A is a F sigma set, A can be written as what? Countable union of closed sets. Fn. Fn's are closed sets. What is the complement of this? Take complement on both sides. Union n from 1 to infinity, Fn complement. Union becomes intersection, Fn becomes Fn complement. So Fn is closed, complement, Fn complement becomes open. Because the complement of a closed set is nothing but an open set. So A complement becomes what? Countable intersection of open sets is nothing but G delta set. So here is the definition. A set which is a countable intersection of open sets is called an G delta sets. Here G stands for intersection and G stands for open. So that is, it is the countable intersection of an open set is nothing but a G delta set. So here Q is F sigma set. What is the complement of F sigma? Is nothing but irrational number. So which is G delta. So Q is F sigma whose complement is irrational, which is G delta. So that is set of all irrational numbers is an G delta set. So next, an example of a set that is both F sigma and G delta. Here is the example which is both F sigma and G delta. So that is open closed interval. Open closed interval. Why? So this open closed interval can be written as countable intersection of open interval. Here A is already open, so take that as it is. For B, to include B, take one step extra, that is B plus 1 by n. Here B is here, B minus 1 by n here, B plus 1 by n is here. Here B is closed. For that, take B minus 1 by n and take as open interval. And now for AB, open at A, closed at B. So it is countable union of what? Closed set. To show that it is closed, to mark it as closed, take, here B is already closed. So no need to take any element other than B. So here to closed, what should we take for to open A? So A, here A minus 1 by n, here A plus 1 by n. So take up to here, closed up to A plus 1 by n. Up to A plus 1 by n means up to A plus 1 by n, not A. So closed A plus 1 by n, comma B. For both F sigma and G delta set. So F sigma and G delta sets are Boral sets. Why it is Boral set? Why it is Boral sets? So to be a Boral set, it must be an element of cursive B. Cursive B is the smallest sigma algebra which contains all open set and all closed set. It is open sets and all closed sets. This open sets is clearly an element of B, and also the Boral sets, the collection B is a sigma algebra, therefore it is closed under closed under countable union and also closed under countable intersection. That's why F sigma and G delta are Boral sets. That is the reason. So next, AN belongs to a sigma algebra. AN belongs to a sigma algebra. The question is, AN belongs to A, then is it intersection of AN is also belongs to A? So the reason, AN is belongs to A is a sigma algebra means whose complement is also belongs to A, because every sigma algebra is an algebra, therefore it is closed under complementation. So union of AN whole complement n from 1 to infinity is also belongs to A. AN is belongs to A, it means what? Since A is a sigma algebra which is closed under countable union, therefore it is belongs to A. And also it is closed under complementation, therefore it is closed under complementation. Take the complement. What is the complement of this? Intersection n from 1 to infinity AN. AN complement whole complement is AN itself, therefore it is belongs to A. So if you take AN belongs to A is a sigma algebra, then A is closed under countable intersection also. Next problem. Give an example of a set which is both F sigma and G delta. Take the example has open at 0, closed at 2. The open at 0, closed at 2. Why? Because it can be written as countable union of closed set. To closed set, take 0 plus 1 by n, and this one is closed already. So therefore 0, 2 is an F sigma set. Next, 0, 2 also, it also can be written as intersection, countable intersection of open sets. Open sets, countable intersection of open sets is nothing but what? G delta set. So 0 is open already, so 0 is okay. For 2, including 2, so take 2 plus 1 by n, one more point extra, that is 2 plus 1 by n. So then it becomes open. So this is the trick. So what is the trick here? Here the trick is, so take like this. So this is the trick. For open closed, for open sets, take one more extra point, that is b plus 1 by n, then it becomes open. To closed set, to don't include that A, take A plus 1 by n. So that is A plus 1 by n for this. So this is the trick.